Hi guys, it's a great pleasure to be here at Wargaming. I don't know if you realize it, but we have a great partnership and friendship, I should say, that has developed through a number of years. We are currently designing a cool new degree together with a few people, including Stefano and Liko and Aidan and Tom, I believe. This degree is called Bachelor of Entrepreneurship in Games Design and Simulation, so something quite revolutionary where students not only learn how to build games, but are also forced to create a gaming company by the end of their bachelor with all support of the university. Today I'm going to talk a little bit about the kind of research we do. I know that it was advertised as something on AI, and many people, when they hear AI right now, in the past, in the gaming community, when someone says AI, you would think, oh, that's obstacle avoidance, path planning kind of stuff. Now people think machine learning. So the disclaimer, I'm not going to talk about machine learning today. It's more about simulating societies in virtual reality. I'll just illustrate this concept through a case study of a big project that we are running for quite some time. And also another disclaimer I want to make that you might not be aware of. What we build as researchers is very different to what you build in the industry. For us, it's all the thrill of coming up with a new idea and developing a rough prototype that is something like pre-alpha even, and then letting go. Yeah, so we never deliver the fully fledged working product. We always come up with a good idea, develop a prototype, write a paper about it, moving on. If someone picks it up, then we take it further. Otherwise, it's just a bunch of prototypes that we develop. So yeah, that's another disclaimer. So the project that I'm going to talk about is potentially going to be a game at some stage about the first city on Earth. The city is called Arak. It's archaeologists and historians believe it to be the first city on Earth. It's currently in modern-day Iraq. And we've been trying to build it for quite some time. We worked with some Americans from Federation of American Scientists, and then due to GFC, they just fired the entire department that worked with us, so we had to move on. We worked with some professors from Stanford at some stage, but again, we lost this connection after the GFC. So we are turning ourselves into even people that know a bit of history and travel to museums and things like that. So the game is has currently 3 levels, and we started with 3000 BC, that archaeologists have produced some results of excavations and drew some sketches for us, and we recreated the city based on those, and now we already have 5000 BC and 4000 BC, but they're at various stages of completion. Some are just the buildings without humans. And in a project like that, when the Americans started with it, for them it was important to visualize a city, to show the buildings, but unless you're an archaeologist or historian who is really keen on understanding the advancement of their civilization in terms of buildings, it's not something that you will spend a lot of time on, right? You need some action, you need some humans to show you how they lived back then. So that's where we came in with our AI, right? And initially, we were quite lame. We started it in Second Life. It was buzzing back then, and we thought, oh, that's a great platform. And that was a very lame decision, I have to admit. But we moved on from that. The clicker is a bit funny. So there is some data. There are some settlement maps that we used from historians, and there is a rough idea of how things have to look like. But people know very little. I was surprised how little even professors of Near Eastern Studies in Stanford know about history. You ask them simple questions like, how are these people different to us? Did they use a different set of gestures? Did they behave significantly different? So that's something we want to visualize to our people. They say, we know nothing, right? So it's all a lot of educated guess around it. The way they discover settlement patterns, for example, they just count how many nutshells they have excavated per square meter, and that's how they have a feel for how many people live there and things like that. Yeah. So that's our game. That's our 5000 BC that I'm going to talk about. Before it became a city, it was just 3 settlements. And then we also have 4000 BC that looks like that. We did some work with populating it with humans, and 3000 or 2900 BC, that's where we have the most detailed data. As you would imagine, excavating this place in Iraq is problematic for quite some time. Yeah, so they excavated a little bit, then the war started, and then they stopped excavating, then they came back, and then ISIS started and all that. So it's a problematic area. And that's how our 2900 BC looks like. We received a bit of help with designing the city from Krytek. We have some friends in Krytek. I'm originally from Ukraine, so I have some good guys in the Ukrainian office. Right. So the big question is how to make this city alive, how to populate it. And unlike yourselves in big gaming companies, we don't have the kind of budgets you guys have. We are just, indie researchers, not even indie developers. So we don't have the full-fledged skills of even indie developers. So the ideal situation for us, a two-man band with some students, is to just create a magic button that you push and then the city becomes alive. And our research for a number of years has been towards making steps towards this goal, right? This is just a rough overview of our architecture, but I'll just go through it step by step. So the first problem we have is how do we create a crowd? How do we have thousands of avatars that don't just look like random people or clones, but in a historical simulation, what you want is you want them to look like they're coming from a particular ethnicity. We currently think that people in Iraq had Middle Eastern-like appearance, but they had dark skin predominantly, and even that is a speculation. There is some statement that they were called dark-headed, and that's why people believe they have dark skin, but some other historians object to that. So it's a lot of speculation and a lot of educated guess. So the way we generate our population is we manually design a sample of avatars. You need at least for one age group, at least one avatar, ideally two. And then we've used genetic algorithms. How many of you have heard of genetic algorithms? Some people did. So basically it's similar process as humans. When two people want to have a child, there is a process of some genes being inherited from ancestors by their kids, and we've replicated this process, and that's how we can start with a small sample, a small population, and then propagate those genes and preserve some of the features that are characteristics that define this ethnicity. We can preserve them and we can randomize the others, right? And use crossover and mutation, and in the end receive a population like that. That's the first step, and we've been playing with very different things, not only with appearance, but a similar strategy you can apply for personality. So we want to have agents that have different personalities. Someone is droopy, someone is cheerful, someone is in between. Psychologists are quite good in that respect. They develop quite a few computational models of personality. There is a computational model of emotions that you can look up, or you can ask me about it. And there is a way to even connect the two. If you have a certain personality and an event has happened, like someone pushed you and you are an aggressive type, how you would react. Normally, I know you want to know about technical things. So the way you handle it, imagine a reservoir with water, right? If I'm of an aggressive type, this is my annoyance, right? This reservoir. If I'm an aggressive type and he pushes me, the level increases much more rapidly than if you are a more passive type, right? And when this level reaches a certain point, when it overspills, then I'm showing my reaction to this emotional state of mine, right? And it's all connected to my personality. That essentially just has, in the most common computational model of personality, has just those 5 parameters, which is a number from 0 to 1. So everyone's personality apparently fits within that, each number from 0 to 1. So we played with this idea a little bit, and this is the kind of crowd you receive. If you are interested, you can look up some of our papers we published on this. But then once you've created the crowd, you want them to behave in some way. And we were looking for quite some time, how can you make them automatically behave? And the first thing that you need if you're working in AI, in agent community, the first thing agents need to behave is a goal. That's where it all starts. And we've been reading a lot, and essentially we ended up with the same idea as The Sims ended up. That's what psychology points us to, something like Maslow's pyramid of needs. Many of you probably heard about it. Yeah, so you have lower level needs and then higher level needs, and unless all the lower level needs like, you know, hunger, thirst, and fatigue are satisfied, you don't care about things like relationships and friendship and all of that. If you're hungry, you don't care about your friends. You just have to satisfy that first. Or democracy somewhere, you know, all the way up. Yeah, you have to satisfy lower level needs and then go to the high level needs. And we've created a simulation of that, and we have Julian somewhere in the crowd who was helping us with this, our former student that we proudly outsourced to you. He was a very good student. So that's a starting point. We can simulate something like Maslow's pyramid of needs, and this would give our agent goals. I'm hungry, I'm thirsty, I have to satisfy it in some way. How do I do it? How can I automate? Once I have a goal that I have to satisfy my hunger, how can I work with that? Sorry, again, the wrong way. In a similar way, you can treat each of those drives that your agent has, like hunger, thirst, and fatigue, you can treat it as a reservoir that eventually would overspill and you would have to act upon it. That's when you receive your goal. But then you can follow the Sims approach. And Julian would be the person to talk to you about it if you want more details, because he implemented that bit for us. So the idea of the Sims is that essentially there are state machines associated with every object that can address a particular need. And then they all communicate with you and say, I can address your hunger at 100, I can address your thirst at 50, etc. And then you just aggregate all your current values for all your drives, and you try to come up with the best objects that you should approach and use so that your overall mood is satisfied the best, right? So aggregation of all your drives gives you your mood, a number, and then you can just pick up from all the objects that are broadcasting to you which one to use, and essentially all these numbers will change as a result of that. This is how it's going to work in a very simple scenario, which again I'll point you to Julian for the lack of time if you want to know more about this. But previously to the Sims, we went more theoretical AI way of how to do it differently to the Sims, how classical AI researchers do it. And the way we went, we wanted to handle much more complexity. There are some issues with Sims because essentially it's not a very dynamic approach. The whole thing will be still prescripted with those finite state machines, and it becomes very difficult to change something, right? You add a new object, you add a new role in your game, things become very complex, at least for us. To deal with all that, to modify all those numbers, it's quite dramatic. So the way we go about it is we thought, all right, we're going to have different roles in our society. We're going to have someone who is a fisherman, someone who is a water keeper, someone who is a fire keeper, etc., someone who is a king, and so on. So in theoretical AI, there is a thing called electronic institutions, which allows you to create a computational model of social norms, if you like, right? So rules of society by which society operates. And you can even run this normative system and let agents interact and make sure that everything they do complies with those norms, and you can track their progress. And as you are interested in technical things, what this involves is first you have to specify the kind of roles you're going to have in your society. That's a simple example where there are two fishermen, spear owner and boat owner, and two fishermen wives, firekeeper and water supply, as you saw in the previous picture. So you define your roles, you define how they relate to one another, which roles are not, which roles you can't change into once you become a fisherman wife. You can never become a fisherman again, because something you have to support as well is changing roles. We change roles all the time. Today I'm a lecturer or presenter at Wargaming, tomorrow, or after 8:45 I'm a basketball player, etc. Right? So we keep changing our roles all the way, and it's supported in those theoretical models. The next thing you have to do is you have to specify scenes where in your environment certain things happen and how they are to be enacted, and which roles are accepted in which scene. So you have to physically control that if it's a home or a temple, you can only allow these types of roles to enter this scene. Then for every scene for your environment in general, you have to specify those permissions, who can go in each scene, and we have graphical tools to make all that happen, to define all this. And once you've defined your roles and who can go to which scenes, you have to create a scene protocol. It looks similar to a state machine as you're used to from an agent perspective when you're designing your agent, right? It's classical state machine, but the difference here is you are designing a scene. So things that change the state of the scenes are actions of different agents. So you're looking not from an individual agent perspective, but from a scene perspective. For the fishing scene to evolve, we have to wait for an agent with a role boat owner to enter the boat. Otherwise, we are stuck in this state. Once this happens, we have to wait for the spear owner, and then someone sends a message that we are ready to start fishing, etc. So a scene has its own state, and different agents can enter and leave and can perform actions that modify this state, right? And there are other elements, but the main thing is once it is there, then if your agent playing a particular role, like a fisherman, is hungry, if this system is in place, we can force the agent to come up with what we call a plan, a sequence of atomic actions to satisfy that drive, knowing its role and knowing the restrictions, the normative restriction the institution imposes it. If you're a fisherman, you can only satisfy your hunger in, say, a fishing scene or in a home scene, as in our case. And before that, you have to go to a fishing scene, and there you have to catch fish and then come back to the home scene and cook it on fire. That's the only way how you can satisfy. So you can formalize those restrictions. Once those restrictions are formalized, what can you do? How can you automate this whole process? And the idea is very simple: planning. Probably many of you have heard about planning by now. I gave this talk in Crytek only 3 years ago. No one knew much about planning. That's not because Crytek is bad. That's because it was not in the agenda at all, right? Because 3 years ago, I don't know, maybe some of you knew about planning much. Now people are much more aware. For those of you who don't know it, I'll just very briefly explain, and then I'll pass it over to Thomas, a colleague of mine who has also joined us today, and he's going to talk a bit more about planning and the fun things he did to optimize it. So the idea of planning is, other than creating a state machine or prescribing step by step, if you're a fisherman, then you go here and you do this and you enter this scene and you do that. What you can do is you can annotate your environment in a certain way. And in a classical way, you annotate, let's say, every object with preconditions and postconditions. Precondition is what state must you be in for you to be able to use that object. And postcondition is after you have used that object, how will your state change, right? And then once you do that, you spend some significant amount of time annotating your environment, you have the institution in place. That is also another layer of annotation, if you like. Then what you can do is you can say, okay, I'm hungry. What can I do? And the algorithm, planning algorithm, just using simple brute force search, can come up with a sequence of actions coming from your current state to your goal state in which you are no longer hungry, right? So you generate a goal that you have to satisfy hunger. And here is an example of a potter who just makes a pot and then can swap it for food, essentially later. And here are some objects and some actions basically, like find water. It has a precondition that you have no water, and postcondition that after you exercise this action, you would have water. Or work, the precondition for you to be able to start working, which in this case would be putting a pot or piece of clay on the wheel and starting shaping the pot. The precondition is you must have clay, and the postcondition is you must have pot, etc. And essentially, to come up with a plan like that, I'm hungry, so what I'll do is I add water in the clay, I will mix it, will make the clay, I will work, which is put it on the wheel and would start shaping the pot, and then I'll trade, and then I'll have food, is no longer required for you to program all that, either just as a sequence of commands or as a state machine. The system would automatically find this sequence from looking at your preconditions and postconditions. And normally it goes from here, like have food. What is the required postconditions? I have to achieve the state where I have food. That's how I can satisfy my hunger. What is a precondition for it? I must have a pot. Which action does have this as a postcondition? It's this one, have clay. And then you kind of work backwards. And in the end, you come up automatically with this plan. At this stage, I'll pass it over to Thomas to say a few more words about planning, and then I'll come back with some final comments.
All right, guys, so I'll start with a question. Who here started to develop things for VR? Virtual reality, augmented reality? I have a bunch of hands. So you guys will feel my pain. So we've been developing all these beautiful algorithms for quite some time, right? Let's say 5, 6, 7, 8 years. And then we received our first Oculus 3, right? And we started to see how can we, use our technology inside virtual reality. And we found that pretty much we can't. Because just as AI is really hungry for CPU, you can imagine that all those calculations that we do, they require quite a lot of resources from your memory and whatever. The VR needs CPU and GPU, right? So you combine the two, you end up with nothing pretty much, right? So when we've been measuring the performance and starting to put our agents in the virtual environment, right, in the virtual reality, we could have a game with hundreds of agents running around in the Uruk. We have done another one, which was a simulation of old Australia. Well, in VR, we were going around 20 agents running. This is the frames per second. The frames per second was spiking up so much that after 20 agents, it became unusable, right? We're saying that the minimum frame rate for VR should be around 75, 60 to 75. 20 agents was way too little for us. People started getting sick, fainting. It was not much fun, right? So we went back to blueprints, right? We went back to drawing boards to find out how can we optimize our algorithms, right? Well, you might say here, well, maybe guys, you're rubbish because it has been done before, right? There are companies probably just like Wargaming, but of course there is Assassin's Creed who did successfully generated very, very large crowds, right? They have thousands of agents in 2D, and I've seen running hundreds of agents in VR as well. But the big difference between us and big game studio is what Anton mentioned, it's money. We don't have that much money to optimize. Because, for example, in case of Assassin's Creed, it's not very smart AI. What it is, it's smart optimization. There is really not much AI in their approach. There is quite some, but what is it mostly? It's some optimizations of micromanaging behavior on their smaller grids, right? So that way they can have much larger groups of agents. You can think about we have no organization in our AI. Our AI is completely free thinkers. You just put them in the environment, and they just automatically do all the stuff depending on their goals. So what we've done is we check what is eating the CPU, right? Where are we losing the performance? And so we measured and we found that part of it is combinatorial narratives. That's when you have like open-ended narrative in your environment and you need to somehow evaluate which narrative the agents choose. And we had some other stuff, but we found out that the problem is the planning, right? The moment when agents started to plan, they hogged all the CPU from us, right? So the problem here is, like, this is a very silly example that Anton already showed you. When you create a dynamic plan, you start with the set of actions, and then you have to basically, using brute force, find out which actions you can combine in order to come up with your goal. So in this case, your goal would be to make a pot. So you would start with getting clay, getting water, putting water to clay, making pot, and so on, right? The beauty of dynamic planning, which probably hasn't been stressed, is that each agent, just like humans when we play games, we do have our resources at a given point in time. So this means if I would start with some resources already, for example, I would already have a clay, and the fire would be already on. When I dynamically create my plan, I no longer need to perform 20% of those actions. I can dynamically just omit those actions and create a new plan, right? So that's the beauty of dynamic planning, that it creates really smart plans just like as humans do. The problem is its complexity. If you come to think about it, if you want to create plan of length 5, worst case scenario is you have to consider 100,000 different plans. That's nothing, 5 actions, right? You consider 8 actions in your plan, suddenly you have to go through 100 million combinations at worst plan, right? So, and if you imagine having 20 agents, each of them starting to planning at the same time, which in large societies is nothing, imagine how much CPU and how much memory it takes, pretty much everything, right? So that was kind of what we found out is a problem in VR. So instead, we started to look at optimizations that we can do. One of the most classic ones is something from academia called hierarchical task networks. It's a very large concept, sounds complicated concept, but it's quite simple. Basically, what you do is you separate your actions into smaller groups, right? So for example, you take all those, for example, those 12 actions that you saw before, and you separate them into 3 sub-actions, right? So I'll create my sub-action of pot making, bread making, and fishing, which means also I will have to duplicate some actions. But I'm fine with that, because the moment now I'm starting to make pots, I can omit all the other actions that are happening out there. I won't go into too much details. You can ask me afterwards if you are interested in this. But what it gives you, just as you see, if you're starting a top-level reasoning process, you no longer have to consider 12 actions, but you're only considering 3 actions. So you're going from 12 to the 12 combinations to 3 to the 3 combinations, which is, let's say, significantly lower number. But our biggest contribution in this whole scenario, something that we just published in a couple conferences, was something called, well, it's not case-based planning, but our approach on case-based planning. And the idea here is very simple. If you are programming any kind of video game, any kind of simulation, what you in the long run ended up in the large societies is that agents somehow use the same plans, right? So they plan for the same actions. And the way we've done it is basically we store the plans in the case database. So whatever plans that agents needed to do, we remember stuff like what resources the agents had, what the agent was trying to achieve, what was the state of the environment, and what was the plan that has happened, right? So we have kind of a lot of information already stored in the database. And when agent starts to plan a new thing, I'll just look, okay, who had the similar or who had the same goal as me, who had kind of similar resources, and who was in a similar state of the environment. And all we can do, we can pick up those plans, and we have some smart-ish way of either picking up the full plans and just adjusting them, or even combining the plans. So suddenly we are going from complexity, from exponential complexity to planning, we're going to linear complexity, right? Because all we have to do is just go through the list of plans and then come up with the one that we want to reuse. This is a very complicated graph. I'm not going to explain. I will, happily explain it to you, on a personal basis. But the results are quite impressive for us. We went from 20 agents, usable 20 agents, to around, let's say, 400 agents. So that's already 20 times increase. And it's also somehow spiking there and there, and it starts to spike quite a lot here. But we found out that it's actually not the algorithm that was making problems for us, but it was actually the memory management, the garbage collection of the C# that we've been bumping into with the agent platform that we've been using, right? So we are now working on a high-performance implementation of the agent system that we've been using, and we hope to get rid of the garbage collection problem and hope to end up with thousands of agents, actually. We think it's doable. And I guess this is the last graph, very boring one. And basically, we found out that we've been simulating some agents. In 80 seconds, the agents generated 1,500 plans. And we've seen that most of them we were actually able to reuse from the case database, even in the larger simulation. And only very few we had to dynamically plan. All right, so I'll give it back to Anton. Thank you.
All right. So I'll just finish off. We'll briefly outline a few topics, and if you're interested, I can point you to papers that we've published on this, and I can answer your questions. We had to deal with prioritization of those plans when we we also implemented the classical way before storing all those cases. Things like, okay, I have a plan to work. I'm a potter. I have a plan to work. I have to finish this pot and then trade it for food. But there is a priest that calls a prayer just about when I'm halfway to the pot, right? I walk halfway, and then the priest says, okay, prayer clock. Drop everything, finish doing it. Some magic happening here. Is it money delivery or something like in Woolies? Yeah, so I'm halfway there. How can I not completely cancel my plan, but suspend it for a while, go to the prayer, and then come back and resume from the same point? We did some work on how to make that happen. Then, that's again the wrong way. No. We played a little bit with conversational agents, so we actually had a system back in Second Life that you can log in as a student, come talk to this agent and ask, oh, what's that building behind you? Or what are you doing? What are you waiting for? So we did some work on natural language processing, but an interesting bit here was how would agents understand the environment? How would they be able to talk about what does a building behind you mean? Or a temple behind you? So we've modified, so interacted with natural language synthesis, trying to first understand what is the object the user is talking about. So we did some work on that. If you're keen, we can talk to you about, and this is an idea of how you start separating your environment by coordinate transformation and figuring out these objects to my left, to my right, behind, etc. Pretty trivial stuff, but surprisingly no one has done it before. We also had things like interaction awareness. As you're part of the institution, you are fully aware of this is my role, this is my scene I'm currently at, this is my state. So you would be able to use that to better explain to the user, yeah, I'm just here, I'm a fisherman, and I'm waiting for someone with the role of spear owner to enter the boat, and then we can proceed, right? So even that can be communicated to our students. The idea behind this game, so that you kind of understand the context, is imagine school kids who study ancient history, and this would be one of their assignments. You start in this game, if you finish on level 1 and you end up being a slave as you started, then you fail. If you finish on level 3 and you end up being a king, then you have high distinction, something like that. And we actually interacted with some schools who are happy to adopt it, and if there is interest maybe from wargaming to develop it as a game, we're quite open to share this idea and work together on it. So yeah, there are all kinds of awareness, and that's probably the point. I know that we are going a bit over time, so that's where I would like to wrap up, but I would also like you, as I take questions, and Thomas probably would join me for that, I would just play a little video of our current very rough prototype. Please don't laugh, because we don't have the kind of budget. That's just this team plus Julian plus a few more students. Yeah, so thank you very much for your attention. And no, sorry, before that, another thing that I wanted to briefly talk about is we are organizing a very cool conference. I've been trying to get it to Sydney for almost 10 years. The conference is called Intelligent Virtual Agents, and this is the top conference in this overlap of virtual reality, video games, and AI. The top academic conference happens on the 5th to 8th of November next year. And you are very welcome to attend if you want to publish something, of course. I don't know if that's the thing for you or not. Of course, you're welcome to do that. But there are also ways to collaborate. There are sponsorship opportunities. You can have a stand to advertise wargaming there. So there are all kinds of things. Just talk to us, and we would be happy to have you. I'm already convincing Liko to give a keynote speech. And I set the bar very high for him, because last year we had some Oscar winners giving keynote speeches at this conference, so we are expecting a lot from you, Liko. But yeah, so without further ado,
I'll send an agent.
good. I'll just play a little video, and we will be taking questions as the video plays. So that's kind of ARAC 5000 BC, its current form of those agents just dynamically walking around and eating and sleeping and fishing and doing all the silly things, all based on simulated needs and planning and all of that. Yeah, maybe just turn the music down so that it does not annoy anyone. It's kind of a trick I learned, that if you don't want to receive too many questions, you just play a video, and then people will be so absorbed looking at it that they will not ask questions. It's really cool. Yeah, go ahead.
So as students study that,
Yeah.
how is it updating?
So basically, okay, the question is for those at the front who struggle to hear, how easy it is, you discover a new thing about people from back then, how easy it is to integrate in your system. If it's within the same role, basically it's all about just throwing some objects in the environment and annotating them properly and modifying the institution, right? So the format we go, the way things are in the environment, of course you have to record some animations, of course you have to develop some objects, and then each object would have some, at current stage, XML, or did you change it to something else maybe?
Yes, so it's quite, technologically, it's trivial. It's all you have to do is put the object in the environment, annotate it, what that object does, what is the emotional response that interaction with that object produces, and then you have to include that object in the thinking pattern in the institution. So saying this activity exists and gives you this kind of information. Right? So you have to somehow include it in the so-called workflow.
And if it's something to do with animations, then of course you have to record new animation. That's another cool thing we have. Universities often have those expensive toys to play with. We have the top of the line motion capture suite. If you guys are interested to collaborate with that, you are welcome to come and use it even. No worries with that. So yeah, we normally, what we do, we need to design a new action. We first put a motion capture suit on. We're not animators. We basically just, the reason why we bought the top of the line one is because it needs a little cleaning, the animation. So we just do a few takes to record a clean animation and then just use the one we've produced, and then we do all the annotation around it, and off you go. You change the institution, you create new objects, you record the animations, and that's it. If you do the same with the Sims approach, you would have to redesign everything. You have to readjust all the numbers, because suddenly there is a new thing that affects everyone. And then the tricky thing that Julian will also tell you about is coming up with the right numbers in the Sims. How much, say, food satisfaction will each of the object give? You change this balance that took people months and months to come up with the right thing. You add something new, you have to suddenly redo everything, and that's, for us, it was an impossibly painful process for a team of 2, sometimes 3, sometimes 4. Yeah.
That being said, still this technological bit is 1% of the work, 99% of the work is still animation and modeling. So we still can't get rid of the design bit. Design bit is still the heaviest. Well, we got rid of the technological bit with our work, but we still kind of suffer with the design bit.
Yeah, and you would notice that our animations are not looking the best, and because we are just academics, so.
And you can
please
see
don't
scenes like
shoot
when
us.
We are doing animations of him sitting in the ground milking a fake sheep, and somebody enters the office like, what the hell are you doing here? So, and I'm there recording, it's like, all right, that's maybe awkward.
So there was a question, yeah.
I was just wondering if your patents were up.
Yeah, so I basically just Google for my name and you'll find it, but otherwise I can give you my card and can send you the link with all the papers. Everything is public, so the beauty of research, we have no secrets. I remember at Crytek it was, like you enter in the FBI or something else, NASA, whatever it is, or you can't go here, you can't go there. Here only supervise with 2 people, because what if you're going to steal the secret and leak it to the press and things like that? Wow, what's going on? No, with us, everything is public. We build something, we write a paper about it. You can use it. We sometimes can share the code for you to use it and stuff like that.
And everything is open source as well. I'm pretty sure you guys wouldn't use it because it's not optimal, but it's all out there. It's on GitHub.
You guys mentioned that you did a lot of, it was a very academic approach, and you briefly touched on how Assassin's Creed does a lot of optimizations and has a lot of dumb AI that looks okay. Could you outline the key points that you would have done differently if you were in the game instead, and it didn't have to be completely accurate? What are the key differences?
I'll pass it over to Thomas.
Well, the execution-wise, I think our approach now can match even the game studios thing. What we need is optimizations from the design perspective. So technology, I put my hand in fire, it can be used in video games of nowadays, because with the frame rate that we've measured and the frame rate that we're achieving, making complex decisions in dynamic environments, I'm pretty sure we now have game-ready technology after this last bit optimization. Our optimization, what they need is from the design perspective. So we need much lower polygons, level of distance, all those things. They don't exist with us. We have one avatar which we found free online, and it's the one that we've been using since 2006, right? And has probably 1.5 million polygons, every one of them, right? So basically, those numbers that you've seen, I haven't even measured them in 3D because I couldn't.
So we're programmers, we're not designers, we don't know.
So those are the optimizations that we would search for. We need, skilled designers that can help us optimize the graphical bits. Technology, I'm pretty sure that it would work well.
There was a question somewhere here that I missed last time.
So you had, in one of your example slides, you had like a guy with a boat and a fisherman.
Yeah.
There's two different, how do they coordinate with each other, these two, to actually go out and start fishing?
Yeah, so basically, currently it's a hack. And the hack is this. If you receive a message from the boat owner, you just have to drop everything and comply. Yeah.
How do they say to give the message to each other? It's just like
it's just a simple message. Event, yeah.
But give us only a couple months, because we are currently working on the new version, which is hopefully going to be up soon. We partner up with people from Spanish Artificial Intelligence Research Institute, who are really big in agent coordination and like multi-agent planning. And we are working on a joint paper bringing coordination and multi-agent planning in this environment as well. We kind of had the version but was very hungry, so the performance wasn't really great. So now we are working on a high-performance version, which will be using negotiations and auctions in order to come up with joint plans, right? So you basically throw your idea into the crowd, and then you use negotiation and auction protocols to find the people that they want to work with you on your common goal. So this is part of the future works. I haven't showed you the slides, but hopefully it's going to be out soon as well.
So if you want to read about it now, there is a great work on NASA, how they did the Mars rover. There were many systems like vision system and wheels, and each time the robot has to act, each system makes a bid. How valuable I think it is for me to grab control of the floor. And then there is a manager that collects all the bids and says, okay, camera, go. Something like that. So.
Are these slides going to be online?
We can. Yeah, we don't have secrets. We can give it to anyone.
Sorry guys, I have to stop questions right here because we have another talk, but Thomas is going to stay here a little bit longer, so if you have other questions, you can address it in a personal way. Yeah. And thank you very much, Anton. I know that you have to run away, so...
Yeah, I'm playing competitive basketball and my game starts at 8:45. I'll stay a little bit, but I'll have to rush off.
So definitely a round of applause.